Okay, so last time I had stopped with a particular example. Um, so let's see if we can pull this back up. I actually had the sheet saved from last time, but I don't know what I did with it, so it's okay. I'll just copy it again. So, problem in question is the following. So, I want to find the general solution to the following equation. So y double prime plus 2y prime plus 10y is cosine of 2t. Um, so just quickly, because we actually did the first bit of this last time. So immediately, same exact process as last time. For all of these problems, this is the same process. So constant coefficient, non-homogeneous equation. So I know one way of dealing with this right now, which is key identities. But before I can do anything, so I seek general solution of the form y sub h plus y sub p. So y sub h is the homogeneous solution, meaning the solution to the associated homogeneous equation for this thing. And y sub p is, of course, the particular solution. So key identities is used to find this thing. Finding the homogeneous solution, always pretty easy. So to do that, I write out the characteristic polynomial. So characteristic polynomial for this thing is the following. So it's z squared plus 2z plus 10. Okay. So we saw last time this thing has roots. So it doesn't factor. You could use the quadratic formula if you like, but we can go ahead and write out what the roots are. So the roots are complex, and they are minus 1 plus or minus 3i. Okay. So there's my roots. Now, I have complex roots. You automatically know what the associated homogeneous solution is. So based on this, this is some arbitrary constant c sub 1 times e to the minus t. That's this real part of the solution, or of this root, cosine 3t plus c sub 2 e to the minus t sine 3t. Okay, so this is my homogeneous solution. Okay. All right, so I found y sub h. I need to find y sub p. So this is where it gets a little tricky because, as you might remember from last time, this thing has complex characteristics. So remember, when you're starting this process out, a couple of quantities you always have to write out associated to this forcing function. So those are first of all, the degree, d is the degree. Mu plus I nu is the characteristic. And m is multiplicity. So what is the degree of this thing? Remember, the degree is, this means it's the degree of the polynomial part of this characteristic thing on the right. Okay, so there's no polynomial in t showing up here on the right, so its degree is 0. So d is 0. That's good. As I mentioned before, the higher the degree, the more annoying these problems are. So having degree 0s is as nice as you can get. So the characteristic, you can refer to the previous video to see this general expression for a forcing function in characteristic form. So the characteristic mu plus I nu, looking at this thing, well, the real part of the characteristic is 0 because there is no e to the something t here, right? There is no e to the mu t showing up. So the mu is 0. Nu is 2. So the characteristic mu plus I nu, this problem is 2i. Okay. All right. And then lastly, I look at the multiplicity. So what is the multiplicity of this thing? Well, the multiplicity is 0. The reason it's 0 is because to determine multiplicity, what I'm really asking is what is the multiplicity of this characteristic mu plus I nu as a root of the characteristic polynomial? Well, the only roots of this characteristic polynomial are -1 plus -3i. This isn't one of them, so the multiplicity is 0. Okay. Okay, so now we have those three quantities that we need. All right, so then how do we proceed? Can't hear me. Oh, that's oh. Can you guys hear me? I was just reading comments. I saw that people said they couldn't hear me, but they actually had their YouTube volume turned down. I don't know if that's an issue. I'll have to mess with the gain on my mic. But I'll save that for before next lecture. I'll get that sorted out. So hopefully everybody can hear me somewhat okay. Okay. So I'll keep going, like I said, and I'll check and see if there's more complaints about how quiet I am here in a second. Okay. So I can hear. That's good. Good. Awesome. That's great. Okay. So anyway. All right. So we've seen these three quantities that we need for starting this process. Okay. So then, once we have this process started, or once we have written out these quantities, how do I get this process going? The idea here is I start with the mth degree equation and go to the m plus dth key identity, right? So I begin with the 0th key identity in this case and go to the m plus dth, which is the 0th key identity, which means that according to this, I should only need the key identity itself. Remember, what is the key identity here? So this is the following. So this is all I actually need. Notice that my camera was a little out of sync. Okay. So this is the 0th key identity, and this is all that's actually needed according to my recipe, right? Okay, so then how does this go? So all I have to do now is follow this process that I outlined last time, which is I have this equation, and since I don't need any further equations, all I do is just evaluate at the characteristic. So I evaluate at z equals 2i. Okay. So this is where something kind of weird happens. So I have L of e to the 2it is equal to p of 2i e up to the 2it. Okay. Well, this is a little strange here. Why is this a little strange? So looking back, p of z is this thing, and so computing p of 2i is plugging 2i into this polynomial expression. So I can do that. So I have p of 2i is just plugging it directly into p of z. This is 2i squared plus 2 times 2i plus 10. Okay, so this is 4i squared plus 4i plus 10. Okay, but remember the algebra of complex numbers. I squared is minus 1, so this is actually minus 4 plus 4i plus 10, and so this is actually 6 plus 4i. Okay. Now, of course, you could do this a lot quicker. You wouldn't have to write it out and be this thorough. You can do a lot of this in your head, but I'm just doing this to remind you of how this complex algebra works. So there it is. Okay, so this is 6 plus 4i, and so what we have here is that this is equal to 6 plus 4i, which is just a complex number, times e to the 2it. Okay. So that's what my key identity tells me. How does this help? Well, remember how this process worked when we didn't have complex characteristics. So when we didn't have complex characteristic, the idea was the thing that showed up on the right was supposed to be at least related to this. It didn't have to be in a single step. It didn't have to exactly be the thing on the right, but it had to be this thing, maybe with a constant multiplying it, right? So it needed to be comparable to this thing, this function on the right-hand side. Okay, so where does that come in? The idea here is the following. So you might notice a few things here. One, what is, as I said last time, what is the real part of e to the 2it? Remember what I mean by this. Maybe it's good to do some refresher here. So remember that if I have a complex number, a plus bi, okay, I can talk about the real part of a plus bi. That's just a. And I can talk about the imaginary part of a plus bi. That is b. Okay, this is the definition of these things. It makes sense now to also talk about something else. So one, you understand basic algebra of complex numbers. So you treat the I like you would if it were a variable, with the understanding that I squared is minus 1, right? So that's how this complex algebra works. But practically there's something, so treating I as a variable except I squared is equal to minus 1, that handles doing the basic things that you might want to do with two complex numbers. So for instance, if you have two complex numbers, a plus bi and c plus di, multiplying those together, right, you FOIL those out or distribute those. You can do that. I have no doubt that all of you can handle doing something like this. Adding or subtracting two complex numbers works in the obvious way, but there is something that comes up a lot, and we're about to do it in this example right now, that is not quite as straightforward. So you've probably seen it before in some way, but here it is. It's how to divide by a complex number. So multiplying two complex numbers, that's fine. You know how to do that. But how do you divide by a complex number? That is, what is the multiplicative inverse? I'm writing it bi. I guess I'll stick with that. So what is the multiplicative inverse of a complex number, a plus bi? So how does this work? So the way this works is the following. Maybe it's an easier way to remember this using slightly different notation. So let's call z a plus bi. Okay, so z is a plus bi. Well, z is a plus bi, and z bar is a minus bi. This is called the conjugate. So this is the complex conjugate of z. Okay. I have a joke that I'll tell you about this. Maybe I'll put the joke in a lecture that I'm going to record later and upload. So that'll give you some incentive to watch the lecture and look for the joke. So anyway, so I have complex number a plus bi. Its complex conjugate is written z bar here, and this is a minus bi. Okay, another quantity associated with complex number is its modulus. Looks like an absolute value sign. So what is this? This is the square root of a squared plus b squared. Okay, so reminding you quickly what this is saying. You all know by now that a complex number is just a point in the plane. So if I have the ordered pair in the plane A, B, right, then I can identify this with the complex number A plus BI. And if I call this complex number Z, then what is this modulus of Z? Well, it's just the distance from that point to the origin, right? Okay. Of course, another way of writing this that's often convenient is squaring this modulus so that you get the sum of the squares of the real and imaginary part of that complex number. Okay, so this is called the modulus of the complex number z. All right. Okay. Now, why did I go through all this process? It's because there's a simple way of writing the multiplicative inverse of a complex number z. It's simply z bar divided by the modulus of z squared. Okay, so a couple of things, right? One, z bar is obtained just like this. So if you have a complex number a plus bi, z bar is just a minus bi. So that's simple. You can immediately read off the complex conjugate from some complex number. The modulus, you might note, is not a complex number. It's just this distance here. So it's a real number. It's always a real number. For any complex number, its modulus is a real number. The square of its modulus is, again, a real number. And so this thing you're dividing by here is a real number. Okay. So we'll do an example really quickly. But in terms of a and b, what does this thing look like? So going back up here, 1 over a plus bi, if you like, that's the conjugate of a plus bi. So that's a minus bi divided by the modulus squared, right? So this is a squared plus b squared. So writing this out fully as a complex number, this is the complex number a divided by a squared plus b squared minus b divided by a squared plus b squared I. Now that looks like a complicated way of dividing a complex number, but it's not that horrible. You'll get used to it. Okay, quickly, let me check. Oh my, there we go. There we go. We can hear. You're all good. That's good. Okay, need to turn volume up. Yeah, I noticed that when I looked at the other streams that I was pretty quiet, so I tried to fix it and didn't have much luck, so I'll try to fix it again before Thursday's lecture. Okay, so anyway, so this is how to find the multiplicative inverse of some complex number. Now the reason why I want to do that is the following. Okay, so returning here, I want to write out the real part of this. Oh, well, I do have some other complex number stuff to get at. Let me go back before I return to my problem. Let me go back here. Okay, so There's something that I hinted at or didn't hint at, I actually mentioned before in lecture, which was Euler's formula. So it turns out, maybe I need more room here. It turns out that since, as I wrote on the previous page, you can think of, say, a point here, call this A plus BI. I'll say that's Z. So you can think of an ordered pair in the plane as being a complex number. Similarly, if you look at unit circle, that's a really, really bad circle. So pretend that that's unit circle, or not just unit circle, but a circle in the plane. You can basically write this in another form. Okay, you can write this complex number in another form, and the way that you can write this is really polar coordinates. Okay, so it's really polar coordinates. So in polar coordinates, what are the two parameters that describe polar coordinates? There's this distance. We've already seen what this distance is, but I'm going to call this distance r, right? And then there's this amount, theta. Okay, and so the way that polar coordinates works with complex numbers is I can express any complex number as r e to the I theta, where r, we've already seen, is the modulus of z. So it's square root of a squared plus b squared. And theta, you might remember how it's found. So I can find theta as the arctan of b over a. I'm not even going to write that, but theta is just this angle. Okay. So theta is this angle here. Now, where does the e come from, and what does e to the I theta? What does any of this stuff mean? The idea is to think of this in terms of a circle. So one way that I can describe this point is, if I'm thinking of this as a circle of radius r, I can describe this point in another way. So I can describe that point as r cosine theta, r sine theta. Okay. But the point r cosine theta, r sine theta, if I write that as an associated complex number, then the associated complex number is r cosine theta plus I sine, or r sine theta, sorry. Okay, so that I can factor this r out, and what I get is that this is equal to r times cosine theta plus I sine theta. And this is e to the I theta. Okay, so a way of writing this is via Euler's formula. So Euler's formula says that e to the I theta is cosine theta plus I sine theta. So, for instance, just for practice, what is the real part of e to the I theta? Well, recall, if you have a complex number a plus ib, the real part is a. In that case, this is cosine theta. And what's the imaginary part of this? Again, just for practice, it's sine theta. Okay. So now I've said enough to go back to what I was talking about here. Using exactly this, what is the real part of e to the 2it? Well, it is the real part of, I'm going to write it out like this, even though once you get a hang of this, you don't have to do that. So e to the 2it, that is cosine of 2t plus I sine of 2t. And what's the real part of this? Well, the real part of this is cosine of 2t. Okay. Now, in Dr. Livermore's notes, you'll see when he's going through these examples that he, um, before he starts doing this algebra at this step, he writes the right-hand side. Sorry, he writes the right-hand side in what's called phasor form. I'll get to what I mean by, or what he means by phasor a little bit later. In a couple sections. I'll talk about phasor form and what that means. For right now, you can not worry about that too much. In fact, you don't have to do it that way. You can basically just proceed like you would normally, pretending that these aren't complex numbers, and everything works out. Okay, so what do I mean by all this? Let me move this paper up a bit. Okay, so I'm going to rewrite the key identity that we have here. We have the statement that L of e to the 2it. Here, I need something to write on. There. So we have the statement that L of e to the 2it is 6 plus 4i times e to the 2it. Okay, so the idea in noticing, or rather writing out this thing, or in Dr. Livermore's words, noticing that the phasor form of cosine of 2t is this, is the following. Because L is a linear operator, it is respected by taking real and imaginary parts. So the fact that I have complex arguments here, the fact that I have complex numbers showing up, right? This might alarm you at first, because you have complex numbers showing up in a differential equation that only has real coefficients, and all of the functions involved are only real valued functions. So where do the complex numbers come in? The point is that I can use this fact to pass to an expression that only involves real numbers by applying or taking the real part. What do I mean? I can move inside, I can take the real part of both of these equations. So if I have two equations, or two expressions that are complex, and they are supposed to be equal to each other, then their real and imaginary parts both have to be equal. So the real parts have to be equal. And it turns out that, if you like, you can take the real part of both of these things, and that real part moves inside this linear operator L. And so what this means is L of the real part of e to the 2it is equal to the real part of 6 plus 4i e to the 2it. Okay. Now, the thing is that it turns out that you don't have to do it in this order, because you have already recognized, this is the benefit of following the way that Dr. Livermore does it in his examples. You already know that if what I want on the right-hand side here is cosine of 2t, since that is my forcing function, if what I want on the right is cosine of 2t, then what I could do, so that on the right I have the real part of e to the 2it, which I know is equal to cosine of 2t. I can, rather than writing this expression, I can come back here and say, well, when I take the real part of this, really what I'm interested in is the real part of e to the 2it, because that's just cosine of 2t, and that's what I want on the right. So really what I can do here is come down here and divide both sides by 6 plus 4i. So it turns out that L being a linear operator means that it's linear with respect to both real and complex scalars, or constants. So it doesn't actually matter whether the number you're multiplying or dividing by is real or complex. L is still linear. And so another expression I could write here is L of 1 over 6 plus 4i times e to the 2it, and that is equal to e to the 2it. Okay, so I'm going to ignore this for a second. Oh, I'm off camera a little bit. Okay. All right, and so this is the expression I have. Okay. Now, you might ask a question at this point and say, what happens if you didn't do it this way? What happens if you wrote this second expression out and you proceeded like that? Absolutely nothing. It's the exact same thing. This just might help you organize some of this stuff. So now, following on, this is L applied to the real part of 1 over 6 plus 4i e to the 2it, and that is equal to the real part of e to the 2it. But we've already seen what the real part of e to the 2it is, right? The real part of e to the 2it is cosine of 2t. Now, bringing this sheet back for a second. My right-hand side function is cosine of 2t. Right? So I have found an expression here, this expression, and that expression, when I apply L to it, I get cosine of 2t. So this expression is the particular solution that I'm looking for. So I'm done, technically, all right? But this is no good way of writing something. I want to know explicitly what this is. This confuses me a little bit. It's got complex numbers showing up here, and I said nothing about this particular solution having complex numbers showing up in it. So how does this work out this way? Well, it turns out that this expression, because it's the real part of some complex expression, the real part is always real, and so this is actually a real valued function. But to see that and to see exactly what function it is, I have to actually go through what it is that's going on here. So let's have a look at this thing. So I claim my particular solution, y sub p of t, is the real part of this thing. So it's the real part of 1 over 6 plus 4i times e to the 2it. Okay, now 1 over 6 plus 4i, how do I know what that is? Well, recall previously. Oh, here's exactly how to deal with dividing by a complex number. So what is this? I can rewrite this in the following way. So this is really the real part of 6 minus 4i divided by what? How does this go? So following this formula, this should be 6 minus 4i divided by 6 squared plus 4 squared, right? Okay, and that is multiplied by e to the 2it, which I can write as cosine of 2t plus I sine of 2t. Okay. All right, now this is slightly annoying, but let's proceed here. So, how does this work out? I have, this is 6 minus 4i over 6 squared plus 4 squared. That's 36 plus 16, so that's 52 in the denominator here. So I can actually go ahead and pull that out. I don't need to worry about that. So this is 1 over 52 times the real part of, now this is 6 minus 4i times cosine of 2t plus I sine of 2t. Okay, let's multiply this out. So this is 6 times cosine 2t plus 6i sine of 2t, right? Minus 4i cosine 2t minus 4i squared, right? I'm just going to write it all out. This is 1 over 52 times the real part of 6 times cosine 2t plus 6i sine of 2t minus 4i cosine of 2t minus 4i squared sine of 2t. So we look at this thing, and to make our lives somewhat nicer, I just say, oh, well, I'm only taking the real part, right? So anything that actually has an I here is ignored. What do I mean by actually has an I? Well, these two terms have i's in them. This one you might say has an I in it, but not really, because I squared is minus 1. So this becomes 6 cosine 2t plus 4 sine 2t. So this is 1 over 52 times the real part of this is, again, so this has an I, this has an I, so I'm ignoring that. So I have 6 cosine 2t plus 4 sine of 2t. And that's it. Okay. So we have one more thing to do, of course. I think I have room right here at the bottom. So thus, the general solution is y of t, which is homogeneous plus particular. Let's remember what the homogeneous solution was. I totally forgot. There it is. Okay, so copying here, homogeneous solution is c sub 1 e to the minus t cosine of 3t plus c sub 2 e to the minus t sine of 3t plus the particular solution that we've just found, which is 1 over 52 times 6 cosine of 2t plus 4 sine of 2t. That's it. Now, I know you're probably thinking that seems like an extremely long process. In fact, I started lecturing around 4, and it's almost 4:40 now, so that single problem and the explanation took a long time. But I had to go through a lot of detours, right? I had to talk about complex numbers. I had to remind you about real and imaginary parts of complex numbers, Euler's formula, how to divide by a complex number, all that stuff. So obviously, you're not going to go through that every single time. And believe it or not, when you get a hang for these kind of problems, it's actually a lot quicker. So with these problems, the main thing that will be a hang up is when you have degree that's not 0. That's kind of the only example of really, really annoying stuff. Okay. So I looked in the chat, no questions, that's good. All right, so moving on, let's do another example. I definitely have time. Let me see. Continuing on. Yeah, that's a pretty good example. Okay, so here's another one. Let's see. So find a general solution of the equation x double prime plus 9x is equal to 4 cosine of 3t. Okay. All right. So, in order to see how this works, I know that you're probably sick of this by now. I'm doing the same thing over and over and over again, but that's how these problems go. So, general solution, just to remind you, it's always of this form for these problems, right? Constant coefficient, non-homogeneous. So, general solution is always homogeneous part plus particular solution, right? Okay, and so in order to write out the homogeneous solution, I need to write out the characteristic polynomial as always. So characteristic polynomial, P of z is z squared plus 9. Okay, that definitely doesn't factor, and so I have to find roots. Roots are easy in this case. So roots are plus minus 3i. Okay. Simple enough. Good. All right, and so the associated homogeneous solution is what? Well, this is c sub 1 cosine of 3t plus c sub 2 sine of 3t. Okay. All right, so there's our homogeneous solution. Okay, so particular solution. Again, I know that you're probably sick of hearing it, but let's go through the quantities that we want to write out here. What's the degree of this thing? Well, there's no t showing up here, right? There's no polynomial part of this thing, and so its degree is 0, so that's good. So degree is 0. What is its characteristic? Well, remind yourself what it means for the forcing function to be in characteristic form. Looking at this thing, well, it is 3i, right? Okay, and now immediately you already see what it is I'm going to say here. What's the multiplicity of this thing? So to answer a question about multiplicity, you look at the characteristic. It's 3i. You say, is that a root of the characteristic polynomial? It is. And it's a root of multiplicity 1. It's a simple root. So multiplicity is 1. So degree is 0, characteristic is 3i, and multiplicity is 1. Characteristic is complex, and so you're going to have to do some shenanigans like we just did in the problem I just covered. Okay, so let's go ahead and do that. All right. So what do I do? Again, I now am starting at the mth key identity. So this is the first key identity. And I'm going up to the m plus dth key identity in the list, but d is 0. So I claim I only need a single one of these key identities, and the one that I claim I need is the derivative of the key identity, right? I probably shouldn't have even used scare quotes there, because it literally is, as we saw in lecture, it is the derivative. Okay, so how does this work? Well, let's write out the key identities. So I have the first one. There it is. And then I have its derivative, the next one in the list. So remember how this pattern goes. So this is p of z t, e to the z of t, plus p prime of z, e to the z of t. Now, I wrote this out, but according to my recipe, I'm claiming the only one I need is this one, right? Because this is the 0th thing, this is the first thing, okay? And like I said, in our recipe, we go from the mth to the m plus dth, and so there it is. Okay. Now, let me see if there's any questions before I move on. Why does the particular solution not have a constant? So that's the thing, right? The particular solution is just any old solution to the equation. The arbitrary constants are the things parameterizing, if you like, the solution space for that equation. So they are all that is needed to fill it out. Okay. Yeah, so anyway. Okay, so moving on. Oh, there we go. Okay. So, let's see if this one really is enough. Okay. So, next in my recipe, what I'm told to do is actually evaluate this at the characteristic. So evaluate at the characteristic, which is 3i. Okay, so I do that. So I have L of t e to the 3it, and that is equal to p of 3i t e to the z of t, plus p prime of 3i. Sorry, this z is actually a 3i. Plus p prime of 3i e to the 3it. Okay. So, you might want to take note here before I even do anything. Again, what's the goal here? The goal is that my right-hand side should, so this right-hand side should resemble the right-hand side of the equation here. Okay. So you might think there's some red flags going on here because there's a t showing up here. But you'll see that this is all going to work out. If you follow the rules in that recipe, this is all going to work out, and it has to work out this way. There's no like choice that you have in this process. So here you might notice, what is p of 3i? Well, the multiplicity of this characteristic is 1, which means it is a root of the characteristic polynomial. So when I plug in 3i into p of 3i is 0, right? P of 3i is, I get a minus 9 here. I have 3i squared, that's 9 times I squared plus 9, that's minus 9 plus 9, that's 0. So this is 0. Okay, and so all I'm left with is p prime of 3i e to the 3it. What is p prime? Well, here's p of z. What's p prime of z? I think we can handle computing this derivative. It's just 2z. Okay, it's just 2z. And so this is 2 times 3i. So this is equal to 2 times 3i, that's p prime of 3i, e to the 3it. Okay, so this is 6i. 6i e to the 3it. Now, there's ways of being a little slick here with these constants, but if you don't even care to put, to lift a finger or put in a single ounce of effort when it comes to trying to be slick here, you don't have to. You can actually always do the same thing. So I'm not even going to pay attention. I'm just going to take this 6i and I'm going to divide both sides by it. So I have this expression here, L of t e to the 3it is equal to 6i e to the 3it. I can just go ahead and write, this implies that L of 1 over 6i is e to the 3i, sorry, t e to the 3it is equal to e to the 3it. Okay. So that's what my key identity tells me. Now, again, I want to stress, I want what's on the right here to look like this. Does it? Well, again, what did we do last time? So what we did last time is we took the real part of both sides of this. So the expression we were actually interested in was L of the real part of 1 over 6i t e to the 3it is equal to the real part of e to the 3it. But what's the real part of e to the 3it? I'm not going to bother you with all those details. Again, you know how to do this. E to the 3it is cosine of 3t plus I sine of 3t. The real part then is cosine 3t. So this is cosine of 3t. Okay, so I have a cosine of 3t here. What I actually have on the right here is 4 cosine of 3t. So then how do I adjust this? I would multiply by a 4 here, which means I also have to multiply by a 4 on the left. Because L is linear, I can move that 4 inside. The real part as an operator is also linear, so I can move that 4 all the way in if I like. So, in fact, I'm going to go directly from this expression. I'm going to copy this expression and then do what I just said. So I'm going to just write down exactly the thing that I had before. So I had L of the real part of 1 over 6I t e to the 3it, and that is equal to cosine of 3t. We're almost happy, so I want this to be a 4 cosine of 3t. So there, it's 4 cosine of 3t, but if that's going to be the case, I can put a 4 here. Well, to clean this up a little bit, yeah, 4 over 6, that's 2 over 3. I can actually move that outside of the real part operator and the L operator because they're both linear. And so what I get here is that this is 2/3 times L of the real part of 1 over I t e to the 3it is 4 cosine 3t. Okay, I just wanted to move this 2/3 out to clean this up. In fact, what I did here is actually a little, it's not efficient, really. But I just wanted you to see that sometimes finding the real part of this is actually not that bad. What do I mean? So you have something here, and you might think to yourself, oh crap, I have to do this whole, I'm dividing by I here, right? How do you divide by I? That's, I would have to go through that whole process that I outlined last time, right? I'd have to write out the conjugate and the modulus and all that stuff. You can still do that. It will work totally fine. But sometimes there's some just simple algebra you can do to make your life easier. So what you can do here is note that I can do some trickery. What if I multiply by I over I here? So that's the same thing as multiplying by 1. What do I get here? I would get I over I squared. And I squared is minus 1. So you get a minus 1 here, which I could pull all the way out. And I would be left with minus 2/3 L of the real part of I t e to the 3it. And that is 4 cosine of 3t. Okay. But what is it? So why did I do this? The idea is you can, unless I'm mean and I give you something that is really, really nasty here. The previous one wasn't super nasty, but it was something that it wasn't that nice to do in your head. But in a lot of these cases, a lot of these examples, you'll actually be able to do them in your head. And so I claim you would actually be able to do this in your head when you get used to this, but I'm going to do it out here to show you how you could do it in your head. So you look at this thing, and what you're supposed to think is e to the 3it. I know what that is. That's cosine of 3t plus I sine of 3t, right? But I'm multiplying by t, so that's t cosine of 3t plus I times t sine of 3t. But I'm multiplying by I. And so the thing that would have been the real part becomes the imaginary part, and the thing that would have been the imaginary part becomes the real part. Right? So I'm going to write all that out, but then you'll see how this goes. This is minus 2/3 times L of, what this is the real part of I times t cosine of 3t plus I t sine of 3t. One more is 4 cosine of 3t. Okay. And then this is minus 2/3 L of the real part of, now I multiply through by I, so this is I t cosine of 3t minus, oh, there is no I here, so minus t sine of 3t. Okay, and so this is now the imaginary part, This is the real part. And so what the real part is minus t sine of 3t. So this is minus 2/3 L of minus t sine of 3t. And that is equal to 4 cosine of 3t. And lastly, moving this back inside, L of 2/3 t sine of 3t is 4 cosine of 3t. Okay. And we're done. Okay. So this is the particular solution. All right. All right, so then just writing this out to finish, maybe first I'll say some things. So I claimed at this step, the reason for doing these tricks was quickly being able to do this in your head. Now, I went ahead and did this fully anyway, but how would you do these steps in your head? Basically, you know by Euler's formula, e to the 3it is the usual cosine 3t plus I sine 3t. T multiplying that doesn't change it too much. You can keep track of that in your head. I multiplying that, all it does is change the first bit to being imaginary. The second bit becomes real with a minus sign, right? Because I times I is I squared, which is minus 1. Okay, and so that's all you have to keep track of. And that's why, like, I wrote this out, and it's kind of annoying to write out this many steps. The point of doing this is that you could have actually jumped directly from here to here without too much. You don't have to be like a super genius to do that. Once you do a bunch of these questions, you'll kind of get the hang of it. Okay, I'm going to write it out just for completion's sake. Thus, the general solution is the following. So it is the homogeneous solution. So the homogeneous solution was what? C sub 1 cosine of 3t plus C sub 2 sine of 3t plus that particular solution we just found, which is 2/3 t sine of 3t. Okay. Oh, I was writing totally off camera. There we go. Okay. I see someone said, how do you end up with higher multiplicity? You don't end up with higher multiplicity. I think what you're referring to is degree. And that is something that can happen. So the question was, how do you end up with higher multiplicity? If I go back to the original equation, I'm looking for the general solution of this. And the thing on the right is degree 0, meaning there's no t showing up here. Now, you might have already noticed that there's kind of a pattern here where, oh, the thing that you end up with as a particular solution tends to look like this right-hand side function. So that is true with a lot of caveats. There's a lot of things I would have to say there to make that completely true. But the point is that is definitely almost true, and that is actually the basis of the method of undetermined coefficients, which, as I said, I'm gonna post as like a supplemental lecture. I won't live stream it. I'll just post it at some point. So I will post like a supplemental lecture on method of undetermined coefficients, and then I'm not going to cover it anymore. And so have a look at that. If you really hate this whole process, have a look at that, because a lot of people find undetermined coefficients to be a little bit more intuitive. But I assure you it's the exact same process. It's just disguised in a different way. So anyway, what I was saying is that, yeah, you've probably already noticed that this thing on the right looks a lot like the particular solutions you end up getting. But in this case, as someone noticed, you don't have a t here, but you do have a t showing up in the particular solution. Why is that? That can happen. Unfortunately, that is something that can happen, and it is due to this multiplicity being 1. That's how this happens. It doesn't always happen like that, even when the multiplicity is 1. There's a whole list of rules for the form that this thing can take, and it depends on all these quantities. Okay, but yes, this can definitely happen, and you can actually verify for yourself that this works out the way that it does. Okay, questions. Let me see here. Oh, well, I didn't have to multiply by I over I on the right side because it's just multiplying by 1, right? So if you like, you can say that I multiplied by I over I on the right side, but then I just canceled them out. Okay, maybe let's do, let's see, well, it's already been over an hour, but I could do, can maybe do one more. Okay, so let's do one more example here, and then we'll be done with. Actually, I still need to do a degree positive example. Maybe I should do that. Yeah, let's do that. So here's an important example where the degree is greater than 0. Okay. So every example of using key identities that we've done so far has been a degree 0 example. So the degree was always 0. We only needed to use a single equation in the key identities, and that was it. Okay. So then what happens when the degree is not 0, when the degree is positive? When the degree is positive, you have to use multiple key identities, and you have to combine them in a way to get what you want. What's annoying about this is that it requires the use of multiple equations rather than just one. And you saw that even just using a single equation, at least, when you're at this early learning stage, seems a little tricky. So then using 2 is just a very kind of annoying thing. So let's see how this works when we have to do it like this. So find a general solution of, I used y here even though the problem used x, so there, that looks better. Okay, so find a general solution of x double prime plus 2x prime plus 10x is equal to 4t e to the 2t. Okay. So you might recognize this left-hand side. We did it in an example earlier. So quickly, as always, right, I have a general solution of the form homogeneous part plus particular solution. Okay, to find the homogeneous part, I do the same thing I always do. I write out the characteristic polynomial of this thing. So characteristic polynomial is z squared plus 2z plus 10. As we saw, this has roots -1 plus or minus 3i. Okay, so those are my roots. Okay, now coming to here. Okay, maybe I should write out this homogeneous solution first. So what is x sub h? So using our recipe from the homogeneous case, this is c sub 1 e to the minus t cosine of 3t plus c sub 2 e to the minus t sine of 3t. Okay. All right. So next thing I always do, I look at the right-hand side. I write out the quantities that I need in order to find this particular solution so that I can be done with this. All right, so what's the degree? The degree is 1 because there is a t here, right? If this were a 4t squared, the degree would be 2. Right, so here, degree is 1. Okay, so that is definitely less fortunate than the degree being 0, but that's fine. Degree is 1 here. Okay, what is the characteristic of this thing? So looking at it, I have an E. I do not have a cosine or sine term showing up, so nu seems to be 0. So the characteristic seems to be 2. So it's real characteristic. Okay. So then what is the multiplicity? Well, the multiplicity is 0, right? I can quickly write that out because the characteristic is real, but both of these roots are complex. But anyway, characteristic is clearly not a root of this, so its multiplicity is 0. Okay, so according to our process then, what do? I write out the key identity starting from the 0th key identity, going to the 0 plus 1th key identity. So I go from the 0th key identity, the key identity itself, to its first derivative, and that's it, right? So just reminding you, I have L of e to the zt. This is p of z e to the zt, and L of t e to the zt is p of z t e to the zt plus p prime of z e to the zt. And that's all I need according to this process that I listed out last time. So unlike in all the other examples we've done, I claim that typically I will need to use both of these somehow. Okay, so what do I mean by that? Well, the idea here is the following. So first, I evaluate both of these at my characteristic. So eval at z equals 2. Okay, so evaluating both of these as equals 2, what do I get? The first one is L of e to the 2t is equal to p of 2 e to the 2t, and L of t e to the 2t is equal to p of 2 t e to the 2t plus p prime of 2 e to the 2t. Okay, so these are the two equations I get. All right. So before I go further, let me just evaluate what these things are. So p of 2 is 2 squared plus 2 times 2 plus 10. So that's 4 plus 4 plus 10, so that's 18. Okay. All right. And p prime of z is 2z plus 2. And so p of 2 is 18. P prime of 2 is 2 times 2 plus 2. So that's 4 plus 2, that's 6. Let's put those here. So we have expressions L of e to the 2t is p of 2, which we saw as 18, so that's 18 e to the 2t. Oh, I'm way off. There we go. Okay. And L of t e to the 2t is p of 2, which is 18 t e to the 2t, plus p prime of 2, which is 6, so this is 6 e to the 2t. Okay. So now you might realize what it is that's going on here that is wrong, right? So why is it that in the case where you have positive degree, typically you have to use multiple equations to make this work? So, all right, so here is the thing that we're trying to find the general solution of here. It's a little confusing when I write it like that. So remember, here is the equation we're trying to find the general solution of. The right-hand side function is 4t e to the 2t. Okay. So remember, the entire point of this key identities process is what I get here in my key identities expression. I hopefully should have a 4t e to the 2t showing up. But notice that if I were to just use the second equation, I have 18t e to the 2t. If that was the only term that I had, I could correct that, right? I could multiply by 2/9, right? If I multiply by 2/9, I'd be good to go. So multiplying by 2/9, I would have exactly what I needed there, and I'd be fine. But I have this extra term here, right? And that extra term does not show up here. And if I'm just using this equation, there's just no way to get rid of that term. So that's what I want to do. I want to get rid of this term, and then I can fix this with whatever constant I end up with here. I can always scale it, and this is linear. Everything works out. So I'm fine in that case. But I need to get rid of this. So how do I get rid of this? By using this first equation. All right. Notice if I multiply the first equation by 1/3 and then subtract it from this second equation, what do I get? Well, it gets rid of this, right? Note, right? And this is the reason this is tricky is because how you go about doing this, even though it's completely deterministic, meaning that you're not going to end up with a system that you can't solve. Okay, you will be able to solve this, but you can definitely make your life easier in certain ways. So note that what this tells you is that L of, for instance, 1/3 e to the 2t is equal to what? Well, if L of e to the 2t is 18 e to the 2t, then L of 1/3 e to the 2t is 6 e to the 2t. Ah, that's nice. That means that I can subtract off 1/3 e to the 2t, and it gets rid of this term. So what this means is that L of t e to the 2t minus 1/3 e to the 2t is just 18t e to the 2t. Now I've done something here. I've taken a shortcut in a quick way. I have used the fact that L is linear here. Technically, I've taken L of t e to the 2t and subtracted from it L of 1/3 e to the 2t. So I have L of t e to the 2t minus L of 1/3 e to the 2t. But L's linear, so that's the same thing as just L of this whole thing, right? Okay. But I still need to correct this. This needs to be a 4t e to the 2t. And so to correct that, I multiply both sides by 2/9, move that inside L because it's linear. So this is L of 2/9 t e to the 2t minus 2/27 e to the 2t, and that is 4t e to the 2t, which is exactly what I want. So the particular solution, I used x here, yeah. So the particular solution is 2/9 t e to the 2t minus 2/27 e to the 2t. And you can write out the general solution from there. Okay, so that's a pretty good example of how to use this. Note that it wasn't that painful because this was a kind of a nice example where the arithmetic wasn't too bad. But typically for non-zero degree problems, you are going to have to use multiple equations to get it done. Okay, let's see here. Okay. Will we ever get some awful forcing not in characteristic form? Yes, you will, but that you will have a way of dealing with that. Okay, there's a couple of ways of dealing with that. So when I finish undetermined coefficients, I'm going to mention something called composite characteristic form, which is that is not too bad. That's pretty straightforward because basically what that is you have a forcing function that is not in characteristic form directly, but it's the sum of multiple functions that are in characteristic form. So there is a straightforward but very annoying way of dealing with that, and it's exactly what you think it is. It's you have to do multiple key identities problems basically. So that's one thing. There is another type of forcing function where you're just going to have something that is not in characteristic form at all, and there is a way of dealing with that. We'll do that. That's exactly the next thing that we're going to do basically. Let's see. Can we do one with higher degree? Yeah, we just did one with higher degree. And so let's see here. Can there be multiplicity of 2 or more? Yeah, you could definitely do that. And in that case, your starting point in key identities would be, whatever. So your starting point is determined by the multiplicity, and your ending point is determined by the difference between, it's determined by the degree, really. So if your degree is 0, your starting point is your ending point. If your degree is 1, then you go up 1. If your degree is 2, you go up 2 from your starting point, and so on. Why did I use 2 equations? Because I had to, right? Here I want something that looks like 4t e to the 2t. But if I just use this first equation, that doesn't even have a t in it. I could never get this term. The second equation, if that was all I used, it has the term I'm looking for, but it has this extra term that doesn't show up here. So I have to use the first equation to subtract off that term that I don't like. Okay. Are we going to get problems with degree greater than 1, multiplicity greater than 1? Yeah, you could. Nothing, it won't be too crazy, obviously. It's not meant to be like a really, really tedious thing. So degree greater than 1, multiplicity greater than 1, I could give you degree greater than 1. The biggest thing I would give you is like degree 2. That would be the absolute worst, most annoying thing that I give you. Multiplicity greater than 1, I could definitely do that. Both of those simultaneously I could, but it's the degree being greater than 1 that's more annoying. The multiplicity being whatever is not that big of a deal. Yeah, okay. I think that's pretty much. It does. These don't. Once you get in the habit, once you've done enough of these, it's not as long as it seems. It doesn't take as long as it seems. Like I said, I was going through and explaining every single thing I was doing. If you were just doing this on an exam, it wouldn't take you nearly as long. So yeah, you don't have to worry about that. Oh, well, the thing is that you want to subtract this term off. That's where the minus comes from. You're subtracting these 2 equations, right? But you're subtracting a particular multiple, in this case 1/3. So essentially you're taking 1/3 times this equation, subtracting it from the second equation. That's what's going on there. Anyway, okay, so that more or less finishes key identity stuff. So you've seen enough here that this has covered all the cases. So degree 0 case where you had either real or complex characteristic, you've seen both examples of those. And then this single example of positive degree is a pretty representative example. So your TAs will go over key identity stuff in the office hours / discussion sessions that they're going to be holding tomorrow. So I'm going to post, if you haven't heard from your TAs already, I'm going to post an announcement here in a little bit, maybe 30 minutes, where I will basically tell you how your TA sessions are going to go. Well, so like I said, I know that some of the TAs had already contacted you. Basically, they're going to be held via Zoom. They'll be held on Wednesdays in the afternoon. So for the particulars of that, like I said, look at the announcement that I'm going to make here in 30 minutes. But anyway, so that's the deal. So Thursday, I'll lecture here at the same time. If I need to scoot it back a little bit because I have some other stuff going on Thursday, so I may push lecture may happen a little bit later, or I could just record the lecture earlier and not live stream it. But anyway, I'll let you know all that stuff. I'm gonna organize the this YouTube account so that everything is nice and all my videos for my different classes are separated, and I'll go through and timestamp stuff because I know there's like 5-ish minutes of dead time at the beginning of most of these videos. But anyway, all right, guys, that's it for now. So I will see you all again on Thursday. Tomorrow, like I said, your TAs will hold office hours / discussions. So pay attention to announcements for that. And anyway, that's it. So I'll see you guys on Thursday.